Okay, so we started section 4.2 last time, and we left off at the end of talking about basically like how many numbers do I need to test before I say it's prime and I don't have to keep testing, right? What's the maximum number? We do not want to have to test far beyond what's necessary, but we want to make sure we've tested everything that is necessary. And we had crossed paths with 3 different theorems that applied. Theorem 414 talked about the fact that this is necessary, that the factors come in pairs. And so in some sense, if I've gone all the way down this side, I don't really need to test 24, 12, 8, and 6. They came about on their own, right? Because they came in pairs. So if I've gone sort of all the way down this side and none of those or anything else worked, then there wouldn't be anything on the other half of the side to go to anyway. And if you take a look at the number 24, because I was using an example 24 because we've done 24 back in section 4.1. And we did this theorem that we ran into last time, and we said square root of 24. Somebody tell me approximately what is the square root of 24. We'll just do it with one decimal. It's not a perfect square. 4.9. So if I were looking at this number, the theorem that we briefly encountered last time would have told us we don't need to test any prime numbers bigger than 4.9, which means the number 2 and the number 3 is enough. So if I were trying to decide if 24, which is kind of a funny one to do because we know it's even, but pretend for a minute. If 24 were prime, I could stop after I tested 2 and 3. If 2 and 3 don't work, nothing else is going to work, right? Now, you might say, well, but Dr. Hand's 4 and 6 and 8 all work too. That's true, they did, but if the 2 and the 3 had not worked to begin with, we would have already failed to have anything any further. So the reason, right, that 4 is on there is because 2 was already on there, so 4 stood a chance at being there. Whereas if 2 hadn't been there to begin with, 4 wouldn't certainly be there either, okay? So that's not very far, right? I don't have to go very far. I mean, 24 is not a huge number, but I don't have to go very far before I can make the claim that there's none available, right? None are going to work. And so this is where we encountered those pieces. So theorem 415 was talking about just that. It talked about the fact that if we have a composite number, then it has a prime factor, right? If it's composite, it will have a prime factor where p squared is less than or equal to n. So let's use that factor. Let's use 24. So let's say 24 is a composite number, which it is, and it has a factor, namely, we'll use 3. Then that would mean that 3 squared is less than or equal to 24. So would 2 squared, right? The prime factors that divide 24 fit into this criteria. And on theorem 416, it tells us that if there aren't any prime factors that do this, then it's a prime number to begin with. And we can change our number 24 just slightly to see that, and we could use the number 23. So pause with me for a moment and consider, if I did the square root of 23, what is that one approximately? It's still 4 point something. 4.7. I'd still only need to test then 2 and 3, because those are the prime numbers smaller than 4.7. And if I tested 2, well, 23 is not going to divide by 2. And I tested 3, well, 23 is not going to divide by 3. I don't need to test anything else because there are no prime numbers that I can square and still be smaller than 24 that will also divide square and be smaller than 23, that will also divide 23, okay? So this gives me an upper end of how far I have to test. And so when the numbers get a little bit bigger, like maybe a 3-digit number, because in particular, you look at 967, that's bigger, right? I mean, like that's not the 24. I don't know my multiplication tables up to values that give me anything anywhere near 900 something, right? So what we can do is we can take that 967 and take a square root and get an approximation. So what is the square root approximately of 967? Anybody know? 31 point, what was it? 0.1? Yes? Does anybody know? You're not really talking. Oh, yep, that's what I have. I have 31.09. So 31.1 works great. The question asks, what's the biggest prime number I'd have to test? Well, I mean, we could write all the prime numbers out till we get there, but this one just asks for the biggest one. So what's the biggest prime number that I would have to test to see if it works? 31, right? 31 is prime. So the answer would be 31 here. Not because I sort of rounded 31.1 down to 31, but because I considered what numbers lower than 31.1 are prime, and 31 was one of them. So if this number, instead of saying approximately 31.1, had said 34.1, well, 34 wouldn't work because it's not prime, and 33 is not prime, it's 3 times 11, and 32 is not prime because it's even. The answer would still be 31, right? So you might have to check a few things a little bit down before you make the decision about what the biggest one was. A similar question you could be asked is to simply list all the prime numbers you would have to test, right? If I wanted to test all the prime numbers, I would list them all until I got to 31, and that's when my list would stop. So it's a similar question, but the answer looks a little bit different, right? We would write down 2 and 3 and 5 and 7, and we would stop when we get to 31. Okay, everybody good? That's good news, because 967, you probably thought you'd have to test a lot farther than that. And you don't. You get to stop at the nearest square root prime that's lower. That doesn't come out quite right, but that's the idea. All right. We talked about this last time, but I'm going to revisit it with you this time, partly because it's here in the notes and because I want to remind you of how important it is. So we talked about the fact that the number 1's not prime, right? Do you remember why? That's why we didn't want it to be, but do you remember why it wasn't based on other factors? It doesn't have two distinct factors. When we defined a prime number way back here on the first slide, we said that a prime number has two distinct factors. For example, the number 3 has the factors 1 and 3. But the number 1 doesn't do that. It only has one factor, the number 1. So by definition, and people construct definitions to fulfill certain criteria for reasons, right? So what Katie said is not wrong. It's just that the definition was constructed on purpose then so that it didn't have that feature, right? It didn't have the feature that 1 kind of fell under the definition. And this is exactly why we don't want it to happen. It says to show that if 1 were considered a prime, then every number would have more than one prime factorization. So we're going to do an example and show why this is a problem. We did another one last time. I'm going to use the number 15. So if you were breaking 15 down, what would you get? 3 and 5. Okay? So one prime factorization, the only one really, is 3 times 5, correct? That is the unique prime factorization. But if the number 1 were a prime factor, we would have been able to write this as 3 times. In fact, if you want to write them in order, we could do it in order, like sort of numerical order. 1 times 3 times 5. Well, that's not ideal. Now I have 2, quote unquote, prime factorizations if I call the number 1 prime, right? But it's much worse than that. We talked about this last time too. If I can put 1 1 in there, I can put 2 1s in there. Now I don't just have 2 prime factorizations, I've got 3. How many do I actually have? I'd have infinitely many, right? If this held, I'd have infinitely many because I could put as many 1s as I wanted in between here, right? Wouldn't change it. Well, that's not helpful. So I really only have 1. So some people are like, I think she thinks it's 1. It is 1. There is only 1 prime factorization. And that's what we want this to be. We want this to be a unique thing. And by eliminating or not allowing the number 1 to be prime, it is unique. So we would have infinitely many, and I'm going to put it in quotes because it's not really true, right? Prime, quote unquote, factorizations would exist if 1 were prime. So it's not just like I'd get a couple of them, I'd get infinitely many of them. All right, let's take a look at Mr. Arbor's orchard. Mr. Arbor wants to plant apple trees in a rectangular array. Y'all know what a rectangular array is? We've talked about those, right? If he has 36 saplings, find all possible numbers of rows if each row is to have the same number of trees. Can you picture what it's looking like here? Right? It's what you picture when people plant things typically. I don't know if you guys do any gardening with your family at home or anything like that, but we usually set out all the plants. I'm a little OCD. And all the plants have a place to sit before we ever start plowing in to make sure they're equally spaced, the same number here, number there, or that they're off center from one another if that's what I'm looking for or whatever. So there's some sort of a pattern, and his pattern is he wants them to have even numbers of rows. So he has 36 saplings. How can we figure out the number of rows are possible for his trees? Right, it would be all the different factor, and I'm going to put one more word in what you just said, Jocelyn, pairs, right? We're looking for the actual pairs that it breaks up into each time. So we can kind of do it like we did the number 24 when we were looking in section 4.1 by writing them in pairs. And the first pair, although it feels silly to do it, is 1 and 36. He could do one long row. That'd be a little weird. But maybe he's lining the fence, and that maybe wouldn't be weird, right? It's possible. What else could he do? Right, 2 times 18. Whoa, sorry about that. What else? 3 and 12. Lovely. 4 and 9. And then 6 and 6. And we know we're done because there's no space between 6 and 6, right? Yeah?
But if we want all the possible.
Mm-hmm. So that's a good question. So right now what all we've done is we've listed the pairs, right? This is almost like our work part of the question. We're going to answer the question in a little bit more of a formal way, like with the description. So these are the pairs that he could do. And so our answer would be that he could have rows of, and we're going to do exactly what you said, Ethan, rows of 1, 2, 3, 4, 6. I don't need to list 6 twice. And then, what's next? 9, 12, 18, or 36. Now it's kind of weird to think of it as a 36 rows of 1. So that feels a little bit funny, but technically the way we describe it, it's okay to list it that way. If you didn't list it, it'd probably be okay too, because it does feel a little bit awkward. But Ethan's exactly right. It's not just rows of 1, 2, 3, 4, 5, or 1, 2, 3, 4, 6. It'd also be rows of the other one, okay? So you can think of it sort of as, we think oftentimes of rows and columns, and we sort of think of rows as being sort of left to right. So if we're thinking of like a spreadsheet, and columns being the up and down pieces or whatever. But that's just a convention that we've created, not that it's a formal definition, especially if you're doing it inside of a yard. Like how do you decide where the up and down versus the left and right is? That doesn't make sense. So all of these would be the number of rows that we could have for Mr. Arbor. Okay, last question for today. We have Bob. Bob says that to check whether a number is prime, he uses divisibility rules that he knows for 2, 3, 4, 5, 6, 8, 10. He says if a number is not divisible by these numbers, then it's prime. How do you respond? So this is one of those type C questions. It's the kind of thing that a child tells you in a classroom, and you're like, okay, well, I think it's a good idea when somebody tells you something to try and find something about it that sort of makes sense, validate that they're thinking about something correctly, and then try and figure out whether they are really correct. Obviously, that's important. And if they're not, to try to show them why that doesn't always work. So somebody tell me something good about what Bob's thinking. Say again. He wants to use the divisibility rules, right? And if his number divides by one of these, then he's going to find the value to be composite versus prime, and it's going to be great, right? So if he has a number like 30, this would work just fine. There's nothing wrong with this list of numbers, right? It'd be great, okay? Now then, some of the things he said then will work. So we could say something like this, like, this will work for some numbers. And you can give whatever example you would like. Goodness. I said 30. 30, this would be enough for. Okay? Is it going to work all the time? It's not. So, probably a good idea, especially when we're talking with our students, when we just say it's not going to work all the time, to have in mind some example where it doesn't work. So, can you think of one, Jocelyn?
If you do like 12 times 12, or no, that one.
That one will work. I need need an example. Do you have one?
121.
121 is a good example. How'd you get 121?
I multiplied 11 times
11 times 11. Okay, so for 121, this fails, right? And we want to talk about why. So because none of these numbers will divide 121. But 121 is 11 times 11. So it's also composite. Okay, so that's a specific example. There is a smaller specific example, just one smaller that fails too. Does anybody know what it is? There's two. I didn't think about 49. 49 would be one of them. 77 is another. 49, right? 7 times 7 would fail just like this. And then 7 times 11, which is the one I was thinking of because I was thinking about distinct factors. 77 would fail as well. And there's plenty of others that we could use in that spot. There's nothing special. Well, I won't say there's nothing special, but it's not unique. 121 is not unique. There's plenty of options inside of there that would fail. So why is this failing? We gave a specific example for why this is not going to work, but why in general is this not going to work? Okay, so that would be true for your example of 121 and my example of 77, Rayleigh. But not listing the number 11 would not have caused, if he'd listed the number 11, it would not have fixed the problem for Faith's. So we need something a little bit more general.
He's not checking the prime number. That's less than the square root.
Yeah, he's not checking in particular all the prime numbers he should, right? So because there are prime numbers, he fails to check. It's interesting on this too because he's actually checking things that are not really helpful to check too. Did you notice that?
Yeah, that's okay.
There, he fails to check it. There we go. And so this is not exactly answering the issue here, but it's probably at least worth noting he's also over-checking some values. What numbers does he not need to test from this list? 6. What else? 4 and 8 and, yeah, 4, 6, 8, 10 are not necessary to test. Why? They're not necessary to test because each, and those specific ones divides by 2. In general, we could say they're not necessary to test because they're not prime, right? They're composite numbers already. And so if a number divided by 10, we would have already found that it was divisible by 2 or 5 or both, right? Like that's what would have happened before then. Okay? Alrighty.